Hello everyone, and welcome to another video lecture in trigonometry. Kind of a different one than normal. You can tell that because I've put part 1 up at the top here. So let me go ahead and explain what's going on, what's different. So the brief version of the story is the law of sines is a very powerful tool which works on a lot of triangles, including triangles that are not right triangles. We're going to talk more about that in just a second because that's very neat. But when you start going through the law of sines, you realize that in order to use it effectively, you have to meet certain conditions, and those conditions can then be broken down, or rather the data that meets those conditions can be broken down into 3 cases. Now, of the 3 cases, 2 of them are pretty straightforward once you understand what we're about to write up on the screen, but the third one has some hidden difficulties. It's called the ambiguous case for good reason, and that's all I'm going to say about it for right now because I too am ambiguous. The reason I put this all in front of you right now at the beginning of the video is because, well, when putting together my content, I really only had 2 options. One option was I could make a longer video and put everything all into one lecture video. That would mean that I'd probably wind up with about a double-length video, which means somewhere around 2 hours, which I think is ridiculous. But on the other hand, you guys would have all the information in one spot. The other option was I could split the information into 2 parts. The first part would handle the basic theory and the first 2 cases and maybe even a little bit additional. And then the second part would handle the ambiguous case entirely and dedicate its time to making sense of what's going on there. That means that there have to be 2 videos, which is the bad news. But the good news is each one of them is shorter, and I think that's better because it makes it a little easier to parse through. So that's what I've gone with. For my students at the University of South Florida, remember this is all section 6.2 in our books. And without further ado, I think we're ready to begin. Now, as you may recall from the previous video, I spent a good long time, at least 5 minutes, maybe 10 minutes, salivating over how great right triangles are, and I'm not going to apologize for that. I am not apologizing, because everything I said is true. They are incredible. They do pop up all over the place. They are incredibly useful. They have all sorts of information they can tell us about the real world, but if you think about it for more than even a few moments, you'll very quickly realize a sad truth. Pretty much no triangles are right triangles. By which I mean, if you were to walk out right now, find a situation where you need to know something that involves distances or maybe forces or something along those lines, and you drew the triangle that went along with that information, you'd find out that you weren't drawing a right triangle at all. So to send you out into the real world with information about right triangles only, but not about other types of triangles, wouldn't be super useful of me. And so therefore, I'm going to give you a more comprehensive tool, and that tool is the law of sines. For right now, I've drawn a triangle that only has acute angles, and I want to give you some heads up before I dive into what I'm about to do. So, as in the previous lecture, I am labeling the vertices, the places where I find the angles, A, B, and C. Usually, when I work in these problems, I just call the angle at corner A, A, to keep things easy, and the angle at corner B is corner B. The lengths of the sides are given by little a, little b, and little c, and just like last time, little a and big A are opposite each other, as are big B and little little c and big C. I don't have to write the letters for the vertices exactly the way I've done here. I could choose to put big A at any one of these 3 corners. I could choose to put big B at any one of these 3 corners. But once I've chosen where big A, big B, and big C go, I now know where the sides must go. Also, in this picture, I have split the angle B, probably not in half, but I've split it with this dashed red line that I'm calling H, and I am using that to create 2 right triangles inside of my triangle ABC. So, now that we have the basic setup here, let's go ahead and explain what the law of sines says. The law of sines says that for any triangle ABC, which I denote with the symbol for triangle ABC, it must be true that this 3-part equality holds. Now, what does this three-part equality say? Well, it looks like what it says is sine of a over little a is equal to sine of b over little b is equal to sine of c over little c, like it has to be a chain in that order. But actually, that's not really what it says. If you think about it, equality really means that when I write two things are equal, they are the same as one another. So what I'm actually saying is, if I make a fraction that looks like sine of an angle divided by the length of the side opposite, it will be equal to any of the other two fractions written that way. So sine of a over little a is the same thing as sine of b over little b, but it is also the same thing as sine of big C over little c. Sine of big B over little b is the same thing as sine of big C over little c. Every single one of these fractions is equal to one another, regardless of which triangle I choose. That probably sounds like something of a bold claim, so let me show you why I know that's true, and it comes down to using what I know about right triangles in order to get this information. So to start with the way I've drawn my vertical line H here, notice that if I were calculating, let's say, sine of A, big A, just to be clear here, then I would accomplish that by taking the vertical side h, or the vertical side length, I guess I should say, and dividing it by the hypotenuse of the right triangle that I'm using right now. That would be this right triangle, so that means the hypotenuse in this case is little c. And similarly, if I were to take sine of big B, or excuse me, not big B. In this picture, the way I've divvied things up, it would be big C, and I'd be using this right triangle right here. Then, for similar reasons, I should be finding that h divided by little a is equal to the sine of C. I can also rewrite these things to be a bit more useful. And by the power of video editing and algebra, I've rewritten them now in these blue equations. Apparently, h is the same thing as c sine of a, and it is also the same thing as a sine of c. Now that I have written it this way, I can combine this information. I could write that c sine of a is the same thing as h, and that is the same thing as a sine of c, but I don't really need this little h anymore. For what I'm doing now, little h has served its purposes. I can cut out the middleman and write the slightly simpler format, c sine of a is equal to a, little a, sine of c. And now, using what I know about equations one more time, I can go ahead and divide both sides. First, I'll divide them by c, and then I'll divide by little a. And if I do that, I wind up with the following fraction equation. Dividing both sides by c gets rid of this c. It puts that c, that little c, underneath on the right-hand side. Dividing both sides by little a gets rid of little a on the right-hand side and puts it underneath on the left-hand side. And so I get part of the three-way equation up above. Sine of big A over, whoops, that should be little a here, is equal to sine of big C over little c. That would be the first in the three-way line is equal to the last in the three-way line. And, of course, if I were to take this triangle and break it down a little differently, like let's say if I drew my right triangles along this blue line that I'm creating that splits the angle C, then I could use similar logic and arguments in order to find out that sine of A over little a is equal to sine of B over little b. Now you may be thinking to yourself, okay, this argument makes sense, but you've used a triangle in which all the angles are acute. What happens if we use a triangle in which there is an obtuse angle? And that's a very good question. Luckily, it's not that hard to answer. Scrolling down, I've drawn a triangle that has an obtuse angle, and in this particular case, in order to deal with the obtuse angle, instead of drawing the dashed line for little h inside, I've drawn it on the outside. Now the reason for this is actually pretty simple. If you think about it, little h represents the height of the triangle. In the case of the previous triangle, ABC, the height of the triangle could be found by simply dropping a straight line down from the angle B and the vertex B. However, in this case, with an obtuse triangle, it turns out that to get the height, we need to drop down from the point A, and that gives us the triangle that we see here. A little bit different, and it does require us to be careful, but we can still get the same equalities. Let me show you how that works. Now, if you remember, last time, the right-hand side of the equations we got were a fraction. They had little h on top, and they were divided by the other sides that we needed. So in this case, I have h divided by little c, which means I'm working in this right triangle. And in the other one, I have h divided by little b, which means I'm working in this right triangle. The left-hand side should be sine of some angle. For the first one, that's actually not so hard, because you'll notice if I draw the big right triangle I've created, the angle that I would need would be the angle B, at vertex B. So I would simply write sine of big B is equal to h over c, which is exactly what we would expect to see. However, when I move to the smaller triangle, the one that involves B and h, it looks like the angle at this corner is not going to be c at all. C is inside the original triangle. The angle I'm actually working with is the supplementary angle to C, which means sine of 180 degrees minus C is equal to h over B. Now you might be thinking to yourself, uh-oh, that means that this thing is foiled entirely. After all, this is not what we expected to see inside of sine. However, if you remember, sine has a nice reflection property. If I flip over the y-axis, then I don't change the value of sine when I'm dealing with unit circle trigonometry. When we're dealing with right triangles, or if you want to talk about this in degrees, you could say this a slightly different way. Sine of 180 degrees minus an angle is exactly the same thing as sine of the angle. No change. And the right-hand side will still be h over b. Now I'm ready to rewrite using the power of video editing and algebra once again. I've shown all the steps together here, but it's just like what we did last time. First, we rewrite these so it's h equals things. We set these things that are equal to h to be equal to one another, because they must be, and then we divide by the appropriate values, little c and little b, and we wind up with a fraction exactly like we would expect. Sine of big B over little b equals sine of big C over little c. Looking at it this way, looking over the stuff that we've done and the rule, for any triangle ABC, it must be true that, and then that three-way equation, you may be thinking to yourself, oh man, I can use the law of sines anywhere. Law of sines is almost all-powerful. Well, there is a caveat there, and it has to do with what is useful for us when we're actually solving triangles. For a moment, let's take a step back and think about what's going on. In the triangles that I drew up above, we pretty much assumed that we had all the information we needed. We had access to all of the angles, we had access to all of the side lengths, but that's probably not going to be the case in real life, where we would actually use the law of sines. So let's take one example of a law of sines type equation. Sine of big A over little a equals sine of big B over little b, the sort of equation we might actually use, and let's ponder what we could know that would still let us work with this and make use of it. Well, it's pretty obvious that if I knew every single one of these angles and sides, then it wouldn't really be necessary. I wouldn't need to work with any of this equation, so we can throw that out. If I didn't know any of the angles or sides, that would be useless too, so we can throw that out. In fact, actually, if you think about it, in an algebra equation, we can only be looking for one unknown if we have a single equation. So, for example, if we didn't know what little a was, but we knew what the other three things were, we would be able to use algebra to solve it. So it sounds as if not knowing one piece of information is really the way we should be thinking about this. As long as we know all the information in the equation we choose, except for that one piece. We can solve for that one piece. And I'd like to point something out. Setting up an equation so it has exactly one unknown and everything else is a constant so that we can use algebra, notice the things we have left are two angles and a side opposite one of those angles. I mention that because let's now imagine that we didn't know something else. Last time we pretended we didn't know little a, so that way we could see whether or not we had an equation we could solve. This time, let's imagine we don't know big A. We know all the other things, we just don't know what big A is. Well, once again, we have an equation with one unknown and then three knowns, so we could solve it algebraically so that we would have something like sine of A equals a number. And then, because we happen to know things about inverse sine, arc sine, we could use arc sine to try and get an answer for what A was. Once again, though, notice, when we have A as an unknown, big A, we have three things we don't know. In this case, two of them are sides. However, we end up with an angle, and the angle and one of the sides are opposite each other. I'd like for you to think about this and maybe play around with it a little bit to verify that what I'm about to say is true. But if I choose any two of the fractions from the law of sines and set them equal to one another, and I'm using them to solve an equation with law of sines, then I must always have one unknown, and that will leave me with at least one angle and at least one side, and one angle and one side must be opposite each other. To say it another way, and to put it in writing, we need to have one pair at least of a side and an angle opposite that side in order to use the law of sines to solve an equation. That is the crux of the law of sines. It's the thing we need in order to make use of it. And it turns out that because of that necessary condition, we wind up with three cases for possible data. Number one, AAS data, or in other words, angle, angle, side data. So what this means is that when we draw our triangle out, it turns out that we have two angles and a side. The two angles then are next to one another, and the side is adjacent to one of those two angles. If we have AAS information, then we can apply the law of sines. Number two, ASA data, angle, side, angle data. So in this case, we have two angles, and we also have the side that is adjacent to both angles, in other words, the side between them. If we have ASA data, then we will fulfill what we need to do in order to use the law of sines. And finally, in spooky red, number three, SSA, although some instructors call it ASS, side, side, angle. In other words, we have two sides, and then we have an angle that is adjacent to one of them and opposite the other angle. This is the case that makes up our ambiguous situation, and we're not going to talk about that one a lot. What's important is that you understand that we have to get the right sort of data. Now that we know that, and we know which two we're going to be working with, the AAS and the ASA, let's go ahead and put them into practice with an example. Moving to the next page, we have our problem, our example. Solve the triangle below via the law of sines. So you'll look in there and you'll see that our given data has two angles, A and B, and then the side little a, which happens to be adjacent to big B. So this would fall into the AAS case, and that is okay. That's one of the triangles we can solve via the law of sines, so we're good to go. Excuse me. Now, as I look at my data here, I notice that the things I'm missing are the angle big C, the side little c, and the side little b. I filled in little b and little c here in red, so we know we're looking for them. And remember that whenever I'm solving a triangle, I always look for the easiest one to work with first. And to me, that is clearly the angle big C. I think that is going to be the easiest for a very specific reason. I already know two angles, so all I have to do is say, well, C must be equal to 180 minus the two angles I know, because After all, let me improve that minus sign there, the sum of a, b, and c must be equal to 180. And that's easy to put into my calculator. Pause me now if you'd like to check it for yourself, but, hesitating, the answer should be 105 degrees. Easy enough. Now, out of the remaining information, I'd like to solve for little b next, and I want to use my law of sines, so that means I'm going to need to set up an equation that looks like, and I'll go ahead and set up the skeleton of it here, sine of an angle divided by the side length opposite is equal to sine of an angle divided by the length of the side opposite. Since I want to solve for little b, it makes sense that one of my sides ought to be little b. And if I make this side little b, the side opposite is little b, that means the angle must be big B. All right, now looking through the information I was given big A and little a, so let's use big A and little a. We always want to use given information first. Oops. And rather than putting the number in, let's just put it in symbolically. Okay, if I want to solve for little b, it looks to me like the first thing I'm going to need to do is multiply both sides by little b. If I do that, one side is going to be just sine of big B, because I multiplied by little b and got rid of the division. The other side is going to be little b times sine of a divided by little a. The next step I would do is divide both sides, or excuse me, multiply both sides by little a, because if I do that, then I'm going to reduce this down to little a times sine of big B is going to be equal to little b times, no fraction anymore, just sine of big A. Then I'll divide both sides by big A, sine of big A, excuse me. That will leave little b all by itself, and I'll wind up with something that looks like little a sine of big B divided by sine of big A. At this point, we can put it into our calculators. I am once again going to encourage you to calculate it for yourself. I'm going to give you the answer now. Going with an approximate answer and rounding to 2 decimal places to keep this easy, it looks like we should have 53.54. And since I noticed that A is given in meters, this would also be meters. Now the side we haven't solved for yet is little c. It's the last thing I've got to solve for. Once again, I would start by setting up a skeleton, except I know that one side has got to be little c as my side length, which means big C is my angle. The other side, you may be tempted to use big B and little b, but since we had to approximate little b, let's go ahead and use the information we were given exactly. Big A and little a. So that would mean sine of big A over little a. Now, just looking at what I've set up here, you can see the similarities with what we worked with in the previous step. I trust you guys to follow through those steps and solve it that way. But I'm going to go ahead and show you another way that you can do this. Sometimes people don't realize you can do it this way, so I'm going to give you the keys to the kingdom in terms of fractions. Remember, if I have two fractions equal to one another, then if I take the reciprocal of both fractions, their reciprocals must also be equal. Or, said differently, if sine of c over little c equals sine of a over little a, then the fraction little c over sine of c must be equal to little a over the sine of little a. I mention this because this is a little bit nicer to clean up. Now all I have to do is multiply both sides by sine of c. And so I wind up with an equation that looks like little c is equal to a sine of c divided by sine of a. And it takes visually much fewer steps. The answer we get, however, is still going to be the same, and if I give that to you now, accurate to 2 decimal places, I wind up with 90.16 meters, approximately. All right, let's backtrack. Did we find out what big C was? Yes. Did we find out little b? Yes. Did we find out little c? Yes. So that would make this triangle solved. Cha-ching. All right, that was a nice AAS triangle. Let's go ahead and do now an ASA triangle. Okay, we have solved via the law of sines. We have the angles C and A given to us, and in between them, little b. That definitely makes this an angle, side, angle triangle, and we can begin solving it. Now, once again, we can solve for one of these things, in this case, big B, very easily. So I'm going to go ahead and write that down now, and then let you guys fill in the gaps. It appears to be approximately 41 degrees. Actually, exactly 41 degrees. Nice. All right, we need to solve for sides. Now, we do not know little a, and we do not know little c, so we're going to solve for those, and I'm going to start with little a. Once again, I'm going to go ahead and fill in the correct law of sines based on the information I've been given. I want you to try and figure it out first, so pause me and then go for it. But otherwise, here it goes. There it is. You might be surprised to see me using big B, since I talked just a few moments ago about only using given data. However, because we know that big B is exactly 41 degrees, it's not an approximation, it's okay to use it in this particular case. Also, you'll notice we do not have the length of side C, so using C and little c won't work in this case. We can also rewrite this, and if we do, it looks like that. Now we can rewrite it again. I'm going to try to conserve some vertical space here, so we'll have A equals, looks like it'll be B sine big A divided by sine big B. And then, if we want to get our answer approximately, it will be approximately 24.12. Okie dokie. That leaves only little c to be solved. And I guess I'm going to have to go over here, page-wise. And I'm going to go ahead and do something rather cheeky. And I'm just going to go ahead and write this in the flipped format. Since we know the flipped format and the original as a given law of sines really mean the same thing, there's no problem in me doing this as long as you understand I started with an equation that looks like this and then translate into this one. And I'm doing the same one for C, or the same process for C, just keeping it in my head. Here it goes. All right, just the reciprocal equation to the one we would normally be using. We multiply both sides by sine of C, and so we get little c is equal to b sine big C divided by sine big B. We can approximate this to 2 decimal places, and we will now. It is approximately 33.49. All right. Another example finished, and again, not a super hard one. As long as you remember, we're always going back to this law of sines idea and getting out of the way the easy calculations first. Let's do a more interesting example. Well, maybe I protest too much. This is very much what we were doing a second ago, but with one significant difference. You'll notice here, I have not given you a picture of a triangle to start out with. And so now we've got to put on our big boy and big girl brains, and we've got to actually draw a triangle for this. you'll notice it really doesn't matter too much whether I draw the triangle proportionate to the information I was given or not. I almost never do. Instead, what I wind up doing is just drawing a triangle that acts as a placeholder. It keeps all the information I need to keep track of and shows me the relationships I need to know. So let's see. I'm going to put, just for giggles, I'm going to put A down here like this. I know that's not where it's supposed to go, but I'm doing it because I'm a rebel. And this is 80 degrees. And then up here, ooh, what will he do next? Will be B, and that's 20 degrees. And then it looks like we have little a, which of course would be over here, and it is 100 meters. I'll put the M underneath. Of course, this tells us that the angle C is over here, and the side little c is over here. And from this point onward, this is just a lot of the same work we've already done. So in fact, I dare say we can move through it pretty quickly. You tell me what's going to come first, or rather, do it, because I'm about to. Here it comes. All right, were you correct? C is equal to 80 degrees. Now, I think the next one I'm going to do is, oops, I almost forgot to put in little b down here. Well, that's just appalling of me. Little b is the one I'm going to solve for next, so hopefully that makes up for it. And of course, we can write this equation in one of two ways. Beat me to it. The first one is. The second one is. Rewriting using algebra and doing a little bit of calculation gives us approximately 34.73. Okie dokie, that leaves us with only little c at this point, and by now you know I am a fan of moving directly to the equation that makes the most sense, whether it should be the original setup or the reciprocal equation. I think in this case we're going to probably want a reciprocal equation. Try to beat me to it. Here it comes. Pow! Wham! Shazam! In fact, actually, I can go ahead and make something a little easier. It sounds weird considering that we got approximate answers before, but actually c equals 100 is an exact answer. That may sound a little weird at first. However, if you go back up into our drawing and look, you'll notice that both A and C have the same measure. So if A has measure 100 meters, then so does C. That makes for a nice little trick we can use later, I imagine. Well, I know what you guys are thinking now. Okay, great. We've done a whole bunch of these problems that are kind of just abstract triangles. We draw them, we get an answer. Can we please do something more interesting? We yearn for challenge. And I shall bring the challenge. We have a friend named Angela. She has a house on one side of the river, and her friend Carmen lives on the other side. Angela at A, Carmen at C. Now, Angela knows that if she travels 540 feet down the river, she'll arrive at B, which is Betty's house. She also has used angles at her house and at Betty's house to Carmen's house to try and help us out. So now we're going to try to figure out how far it is across the river from A to C. Well, actually, this picture makes things pretty easy. It looks like we are dealing with another angle, side, angle setup here. And we've already solved for pretty much everything in an angle, side, angle, triangle setup. So all we have to do is apply what we know. Now, you'll notice we do not have quite the information we need yet. We do have enough information to do law of sines, but we're trying to pick it correctly here. Remember, we want to find the length of the side AC, which means, obviously, we're going to need to use the angle opposite that, which would be angle B if we want to make use of it. However, we weren't given the length of the side opposite big A. That side isn't known either. The only side length we were given is this one opposite C. So it sounds to me like we're going to have to figure out what C is first, then we'll use C and the side opposite, and we'll use B and the side opposite it in order to do this problem. Well, we've already done that before, so let's cut to the chase. If I want to know what C is, I simply take 180, and I subtract the known angles, A and B. This should give us the exact answer, 77 degrees. All right, I want to know the length of the side. Well, it doesn't say it here, but that would be little b in our picture. So we want to find the length of the side, little b. And kind of like we've done before, it sounds like the smart way to do this would be to take little b over sine of big B and say it's obviously equal to, or by law of sines, it's equal to, I guess to be fair, little c divided by sine of big C. That's going to imply that B is equal to little c sine big B divided by sine of big C. And before we do our calculation, let's check. It wants us to round to the nearest foot. That's what it says right here. So I'll go ahead and do that. I will round to the nearest foot, and that will be the next number that you see and hear. It is approximately 399. Let me double check that. Yes, 399 feet. So that is the answer from Angela. I forgot her name. From Angela's house to Carmen's house is approximately 399 feet across the river. Fantastic. Now, I know what you're thinking. You're thinking, sir, that was too easy. Let's have a more interesting one. Okay. We have an example that has to do with navigation. We have a ship, and it's traveling due north. It sights a lighthouse here at point A, and it marks its location via a bearing. We'll talk about bearings in just a minute. Then it travels 2,000 meters, and it takes a bearing once again, this time of 63.7 degrees compared to the original 42.3 degrees. We want to round our answers to the nearest meter, and we want to find a couple of things. First of all, how far is it from our second stopping point, the place where we took our second angle measurement, to the lighthouse? Second, if we were to follow the same course, how close would we get to the lighthouse? Now, there is a harder version of this problem in the homework for my students at the University of South Florida, so let's pay attention carefully here. First things first, though, I want to make sure that you understand what's going on. Notice, let's go ahead and use different colors here. So notice originally, it says when we take the measurement the first time, it makes an angle of 42.3 degrees from the direction of travel. Well, there is another way to say that, and I'll go ahead and put that over here. We were traveling due north. If you rotated from that due north setting to the east by 42.3 degrees, we would see the lighthouse. So that bearing, which is what we call it when we give directions this way, would be north 42.3 degrees east. We start facing north, we rotate through this angle to the east. Similarly, changing to blue, you'll notice that later on, at the second point B, we started pointing due north, we rotated through an angle to the east again, and this time the angle was 63.7 degrees. So, if we put this in bearing notation, our bearing is north 63.7 degrees east. This is how we give bearings. North or south typically is the first one, then an angle that we travel through to get to the line of sight, and then the second the second cardinal direction indicates the direction that we rotated in. So, north 42.3 degrees east means we start facing north, we rotate to the right by 42.3 degrees. If this said north 42.3 degrees west, we would rotate to the left, so to the west by 42.3 degrees. I like the way the book has laid it out here, but you are going to be expected in some problems to know bearings, so it's important to see them here. In any case, we may as well go ahead and get on with the problem. So, we know an angle right here at this corner. We know a side length, but the second angle that we have is outside of our triangle. What do we do with that? Well, hopefully those of you watching the video said at once, oh look, if I take this angle and the angle inside the triangle next to it, they're supplementary. So I can figure out what this angle is. All I have to do is take 180 and subtract 63.7. And indeed, if you do that, you're going to get the angle 116.3 degrees. Fantastic. Now that we've done this, you'll notice that suddenly we went from an angle and a side adjacent, which doesn't really tell us anything, to an angle, a side, and another angle, with the side being between the two of them. This is definitely law of sines, so now I can go ahead and do part A, which I'll start up here. We want to figure out, according to our directions, how far it is from point B, where the boat is, to point C, where the lighthouse is. And it looks to me like, for that purpose, kind of like in the previous problem, we're going to need the angle C at the lighthouse. So that would be this angle, which I've marked with 3 curved lines. That way we have an angle and a side opposite, and we have an angle, and we'll figure out the length of the side opposite, that one, for solving purposes. Okay, once again, if we're solving for the angle at the corner C, we can get an exact answer by doing the following. And if we do that, it looks like our answer is 21.4 degrees. Now we want to solve for the length of the side between B and C. We may as well call that little a here. That makes sense. And if we want to solve for little a, just like we've done in the previous problems, we'll set up the reciprocal equation from law of sines like follows. In this case, little c represents the side opposite big C, as usual, and is 2,000 meters. So, using some algebra, we have little a is equal to c sine of big A divided by sine of big C. And so we're going to get an approximate answer of 3,689. And this is all in meters, so meters. Awesome. Now the next question is a little bit more interesting. It says, how far will you be if you follow the same course? Oh, well, I guess let me rephrase that. How close will you get? How close can you possibly get if you follow the same course? Now, normally that might be a little bit of a head scratcher. However, if we keep following this course, you'll notice that they've put in the point D over here if we continue. The line that connects a straight line, like the one we're making, to a point and makes a right angle to the straight line, which is exactly what's happening here, is the line that gives us the shortest distance. It's an easy to verify geometric fact. So what we're really looking for is the length of the side between D and C. Now, there are a couple of different ways that we could potentially do that, but you'll notice that once we get to the point of saying, well, I want the length of the side between D and C, we have a right triangle. In fact, we have a couple of right triangles, so we're spoiled for choice, but in one of them I have more information. Notice in the right triangle made by D, B, and C, I have a hypotenuse length. We just solved for it in the previous problem. So, if I want to get the length of the side between them, and I have a right triangle and a hypotenuse, surely what I should be doing is saying, hey, look, sine of this angle here, 63.7 degrees, is the side I want divided by the hypotenuse. So what I'm going to do is say that if I take the length of the hypotenuse, little a, and I multiply it by sine of 63.7 degrees, then it should be equal to the length of the side between D and C. Now, since I don't have a name for that side like I did for little a and little c and little b, I'm just going to call it the line segment DC, and I'll put vertical bars around it to denote I'm talking about the length. If I want to find out this answer, I just put it into my calculator, and so I wind up finding that the answer is approximately 3,307 meters. I wrote on a funky side of my approximately equal sign, but that's okay. The work is all good. Now, I know what you're thinking. You're thinking to yourself, sir, we've had a couple of good problems here. Can we have some more? Well, we can have one more, but unfortunately, if I go too much longer, we're going to be a full-length video, and I'd prefer to keep it smaller rather than longer. So I'll give you guys some extra problems when I publish the notes. Instead, let's talk about this problem. We have a parallelogram. It's 60 inches long on one side, and it makes an angle of 28 degrees and 42 degrees with the two diagonals. What are the lengths of the diagonals? Round each answer to the nearest tenth of an inch. Well, okie dokie, let's sort through that information. So when I say a parallelogram, what I mean is what you get basically when you take a rectangle and you sit on it, and it ends up kind of leaning to one side like so. Not perfect, but it's okay. Now there are going to be two diagonals here. One diagonal is going to go from this corner to the one opposite and above, and then we're going to have another diagonal that goes this way. Like so. Now when it talks about making angles with the diagonals, what it means is that when I put my side in here, it says a side of 60 inches long. I'm going to choose it to be this one down here. I could choose it to be one of the other ones, but this one makes sense in my picture. That side of 60 inches makes angles of 28 degrees and 42 degrees with the diagonals. So in other words, an angle here of, to me this one looks like the smaller one, so 28 degrees. Although if I put it on the other side as 28 degrees, it wouldn't be a problem. And an angle on the other side of 42 degrees. Like so. And from this information, we want to figure out the lengths of the two diagonals, rounded to the nearest tenth of an inch. Whew. Well, that sounds a little bit challenging at first, until you noticed a couple of things. So, the first thing that you'll notice is that I'm making a triangle right here with angles at the corners of 28 degrees and 42 degrees. And, moreover, it is one that law of sines applies to. See, I have angle, side, angle information. That means that part of my information for, say, the red side is going to be contained right here in this triangle that I've drawn. Part of it is here. Similarly, part of the blue diagonal has its length given here. The other triangle that I'm going to need, because you'll notice I haven't got all of my information from this one triangle alone, is going to be given up here in the triangle above it. So basically, if I can figure out the length of the red segment in the lower triangle, the one that I'm looking at right now, and then add it to the length in the upper triangle, I'll have the length of that diagonal. And similarly, I find the lengths here for the blue diagonal in this triangle below and this triangle below above, add them together, and I'll get my answer. I'm going to take that in steps, because it sounds at first glance like a lot of work, but it won't be too bad. Since I have got law of sines information, it sounds to me like if I want to get the length of this red side here, I better be using law of sines. And just like the last time that I did this, since it's angle, side, angle, I better find out the angle here that I've indicated with three curvy lines. Luckily, though, that's not going to be too bad. If I call that angle, let's say C, just to keep things easy, then C should be equal to, well, it looks like, once again, it'll be 180 minus the two angles that I know, which are 28 degrees and 42 degrees. And if I'm not much mistaken, that difference is going to be 110 degrees. Now the side length that I want to get for right now is going to be the red one. And I guess if I'm going to go ahead and name these things, I may as well put these things down now. I'll call this bottom left corner in red A, and the one on the right in blue B. Okie dokie. It looks to me like if I want to find the little b segment, which actually I should do in red since that side is colored in red. If I want to figure out the length of little b, I better use big C, the side opposite, big B, and the side opposite. So, in other words, we should get little b over sine of 42, although actually I should go ahead and say here sine of big B is equal to little c, which is what I'm going to call this side over here, equal to 60 inches, divided by sine of big C. And now this looks like things that we've done a whole bunch of times already. I simply write b is equal to, I multiply both sides by sine of big B in order to get to this point, so I should have, keeping to my color code here, I have to be fashionable, little c times sine of big B divided by sine of big C. And that's going to wind up giving me, well, it's going to give me an ugly answer. I may as well go ahead and record it out, quote unquote, exactly like so. It's going to give me 42, the answer to life, the universe, and everything, 0.7244, and then it just kind of keeps on going. So I'm going to put ellipses there to indicate the fact that this is an exact answer that I can only kind of duplicate. All right, that's all good so far. Now it sounds like we have to do a lot more work until suddenly we notice something. If you look at the way that we've drawn this parallelogram, notice that when I make an angle down here at the corner I've designated B, and it gets an angle of 42 degrees, because this is a parallelogram, meaning this side here up top and this side here on the bottom are parallel, one of the properties of geometry says that this angle up here, let me go ahead and do it in blue, this angle up here should also be 42 degrees. And actually, this angle over here at the upper right-hand corner should be 28 degrees for the same reason. This one straight line, doesn't look very straight in my picture, intersects the corner here and here between two parallel lines. So this angle and that angle must be the same, which means the angle where the two diagonals intersect must also be the same as what we calculated before, which makes sense in our picture, geometrically speaking. Wait a second, that means that the length little b that we calculated is exactly the same as the red length, the other part of this diagonal in the second triangle. So actually, if I want to know the answer for one of these two diagonals, all I have to do is say that the diagonal, I'm going to call it diag 1, should be equal to 2 times the length we just calculated from here and here. And that gives us, if we round to the nearest tenth, approximately 85.4, and I believe these were inches. Yes, inches. I should go ahead and point out here that the other part, the part I haven't written down, but should be obvious from the picture, is if the bottom horizontal line is 60 inches, so is the top horizontal line. Well, awesome. Then if I want to do the blue line, now I should just have to duplicate my work. I already know what C is, so all I have to do is set up the rest of my angles to make this work. And I guess, since I seem to be out of room, I'm going to do this in the upper right-hand corner. So, Bear with me. Let's start putting our information there. Using the symbol little a to mean this blue side down here, the first half of my diagonal, I have my equation. Little a over sine a should be equal to little c over sine c, which gives us little a is equal to little c sine of big A divided by sine of big C. And if we feed that to our calculator, we get the exact answer, 29.9760, etc., etc. Once again, thanks to geometry, we have found out that the length of the blue side in my lower triangle is the same as the length of the blue side in my upper triangle. So if I want to get the length of this blue diagonal, which I'm going to call diag number 2, just to keep with the pattern, it should be 2 times the length of little a. And if we do that calculation and we approximate, must remember to approximate to a tenth, we wind up getting approximately 60.0 inches after we round to the nearest foot. So there we have it, our two diagonals, 85.4 inches and 60.0 inches approximately. Well guys, that is as much time as I want to dedicate to this video right now. Any longer and it's going to be unwieldy, and we've already gone longer than I wanted. Watch out for the next video. In that next video, we will do the ambiguous case and we will do some area formulas. Until then, happy math.